Hello everyone, welcome back. Today I will take you through a full walkthrough of avionics system, design, development, and integration, with a special emphasis on the use of simulation tools through every stage of the life cycle. My goal is to explain every major step and concept clearly, so by the end you'll understand how avionics systems are built, verified, and certified, and why simulation is indispensable. Let's begin with a clear definition. Avionics refers to the electronic systems that support an aircraft's operations. Think communication radios and SATCOM, navigation systems like GPS and INS, flight control systems such as fly-by-wire and autopilot, cockpit displays like EFIS and HUD, monitoring and health management systems, and the data management and bus systems, ARINC, AFDX, MIL STD 1553B, that glue everything together. All these pieces must operate as a cohesive, reliable whole, and designing that whole is what avionics system engineering is about. The design process follows a systems engineering approach, a structured life cycle that starts with requirements, becomes functional decomposition, architecture design, simulation and validation, integration and testing, ends with certification. The high-level flow is requirement capture, functional decomposition, architecture design, subsystem development, integration, verification and validation, and certification. At each step we maintain traceability, meaning every requirement maps to design elements, code, tests, and evidence, because avionics are safety critical. Now, before diving deeper, it's important to list the main design considerations engineers keep in mind. Avionics must meet rigorous certification standards, primarily RTCA DO 178C for software and DO 254 for hardware. The design must provide redundancy and fault tolerance, handle strict weight and power budgets, be electromagnetically compatible, and be scalable and upgradable. These constraints influence architecture choices, whether to use integrated modular avionics, M.E distributed electronics, or dedicated line-replaceable units. Next, let's walk through development. Starting with software under DO 178C, the DO 178C process is tightly structured and divided into several principal stages. First is the planning phase. Here you prepare all the certification artifacts. The plan for software aspects of certification, software development plan, software verification plan, configuration management plan, and similar documents. These documents describe how you will produce, verify, and control software artifacts so they satisfy DO 178C objectives. Second is the development phase. High-level requirements are decomposed into low-level requirements. Software architecture is defined with an emphasis on determinism, modular decomposition, and traceability. Development must often occur in qualified tool environments. Compilers, code generators, and model tools need qualification evidence when they affect certification objectives. Third is the verification phase. Verification is requirements-based testing plus structural coverage analysis. For airborne software, you typically need statement, decision, and MC/DC coverage depending on the software level. Verification includes unit tests, integration tests, regression tests, and robustness testing against invalid inputs and fault conditions. Formal reviews of requirements, design, and code are part of this stage. Fourth is configuration management, where every artifact version, requirements, models, code, tests, and binaries is uniquely identified and traceable. This prevents unauthorized changes and supports reproducibility. Finally, certification and quality assurance compile all verification evidence into a software accomplishment summary and other deliverables that authorities like FAA or EASA review to grant approval. B for hardware, DO 254 provides a parallel assurance framework. DO 254 focuses on airborne electronic hardware like FPGAs, ASICs, and complex PCBs. It mandates comparable planning, requirements decomposition, verification, and configuration control, with attention to hardware lifecycle specifics such as manufacturing variants and silicon revisions. C for software, avionics software development integrates model-based design, MBD methodologies using industry-qualified tools to reduce human error and improve verification efficiency integration, combining individual avionics subsystems into a complete, functioning architecture that meets mission and safety goals. It can be categorized into three types. Functional integration, grouping multiple functions on shared compute, as in M.E physical integration. How hardware is physically mounted, cooled, and powered, information integration. The data architecture that enables subsystems to exchange information reliably using ARINC 429, MIL STD 1553B, AFDX, and other protocols. Integration strategy may be incremental, add and test subsystems one by one, or follow top-down or bottom-up approaches depending on risk and schedule. Let's talk about the role of simulation tools more concretely. Simulation helps manage complexity. It allows early error detection, catching issues in model or architecture before they propagate into code and hardware. It supports safety cases. You can exercise failure modes, degraded operations, and emergency scenarios that would be too risky or expensive to attempt physically. Simulation reduces cost and time by substituting expensive prototypes and flight hours with repeatable virtual tests. Now let's dig into each simulation fidelity and what it's used for. Model-in-the-loop ML. It validate algorithm correctness inside the modeling environment. This step is about functional correctness before any compilation. A major enabler across modern avionics development is model-based design, or MBD. Instead of writing every line of code by hand, engineers model system behavior, plant dynamics, control algorithms, signal processing, using tools like MATLAB/Simulink or SCADE Suite. The MBD workflow contains several phases. Plant modeling. Develop a mathematical representation of the aircraft, sensors, actuators, and environment. This can be based on first principles or system identification. Controller design. Develop control and signal processing algorithms against the plant model, refining gains, filters, and logic. Simulation. Run model-in-the-loop ML tests to validate algorithms, then perform software-in-the-loop (CL) tests where generated or handwritten code is executed on a host. Proceed to processor-in-the-loop PyL and hardware-in-the-loop (HIL) as fidelity increases. Code generation. Automatically produce production-ready code from verified models using tools like Simulink Coder or SCADE KCG, reducing manual coding errors and improving traceability. Software-in-the-loop (CL). The compiled software or generated code runs on a host machine, interacting with the plant model. CL checks correctness of the compiled software and higher-level integration issues that appear after compilation. Hardware-in-the-loop HIL. HIL is the gold standard for integration testing. The real avionics hardware, the device under test, is connected to a real-time simulator that emulates sensors, actuators, and the aircraft. HIL validates real-time performance, I/O interfaces, timing determinism, and hardware-software interaction under nominal and fault conditions. Processor-in-the-loop PyL. Here the code runs on the actual target processor or an equivalent processor environment. PyL demonstrates that timing, floating point behavior, and instruction set effects are acceptable. System Integration Simulation or Avionics Integration Simulation Systems, AISS, combine multiple HIL rigs, virtual simulators, and networked components to validate end-to-end system behavior across subsystems. Flight control, navigation, displays, and mission computers. Across verification and validation, often abbreviated V&V, we use a mix of static and dynamic techniques. Static analysis tools such as Polyspace, LDRA, or similar detect runtime issues like overflows or unreachable code without execution. Dynamic verification covers requirements-based testing. Test cases derived directly from requirements, robustness tests, stress tests, and coverage analysis to achieve MC/DC where required. Validation confirms the system meets operational needs. Scenario-based testing, HIL runs, and ultimately flight tests with instrumentation to capture system behavior in real operations. Common simulation methodologies include the MBD workflow I described, plus CL, PyL, and HIL. Tools used in industry reflect these needs. For model-based design, MATLAB/Simulink, MathWorks, and ANSY's SCADE suite are standard. SCADE is often used when certification objectives require tight traceability and certified code generation. For real-time HIL, DSBACE, SpeedGoat, and OpalRT are widely deployed for executing plant models in real time and interfacing with avionics hardware. For system engineering and mission analysis, ANSY's SDK and Cameo systems modeler help with mission-level modeling, trajectory analysis, and system of systems design. For multi-physics simulation, thermal, aerostructural, electrical, SimCenter AIMSIM, and Dassault SIMULIA are used where fluid, thermal, or mechanical coupling matters. For communication and protocol testing, specialized bus analyzers and emulators for ARINC 429, MIL STD 1553B, and AFDX validate message timing, latency, fault tolerance, and arbitration. Examples of typical V&V and simulation test cases include injecting a GPS outage to verify navigation fault handling and cross-check algorithms, forcing a sensor bias or spike to validate filter and fault detection responsiveness, simulating stuck actuators or control surface failures to verify redundancy and degraded modes, validating timing budgets under peak processor load using PyL or HIL, and stress testing the data bus to examine latency and message loss under heavy traffic. Let me also emphasize advantages of the model-based and simulation approach. Early detection of design flaws through executable specifications. Automatic code generation reduces manual errors and preserves traceability. High-fidelity HIL tests verify real-time constraints and hardware-software interfaces. Simulation supports certification evidence by providing repeatable test artifacts and logs, and the approach shortens development cycles and reduces cost. Finally, a few practical points and best practices to keep in mind. Qualify any tool that influences certification objectives. Maintain strict configuration management for models, code, and test harnesses. Plan verification early so test cases and coverage requirements are designed along with requirements. And use incremental integration. Start small and expand complexity once the basic blocks are proven.